we're going to talk about normal probability distribution.
We are going to start with the first chapter, namely chapter 6, normal probability distribution. We want to answer the following. What percent of normally distributed data value lie within 2 standard deviation to either side of the mean? The answer is about 95%. If we want to precisely calculate that, we use the following methodology. The probability of a z between -2 and 2, which is probability of 2 minus probability of -2 if we go with the graph. And we end up with 95.44%. I hope everybody remembers the empirical rule, starting from the mean, go 1 standard deviation on both sides. It covers about 68% of the data. 2 standard deviations away covers about 95%. Where does it come from? Normal distribution, the table, or technology. For a continuous random variable, the probability of a single value of x is always 0. The reason being because it is area under the curve that represents probability. The total probability is equal to 1. The total area under the curve is 1. If you have a single value, it doesn't cover any area, and therefore it's 0 for any continuous random variable. Normal distribution happened to be one of them. And the parameters for normal distribution happen to be mu and sigma, the mean and standard deviation, and the values for standard normal distribution, also known as S and D. We have the values of mu equals 0, sigma equals 1. So S and D for short. We want to find the value of z for a standard normal distribution such that the area in the left tail is 0.05. I want to show you how to use the table. Needless to say, you can also use technology. But as far as the table goes, it's a good practice to start with graphing. So we want the area to the left to be 0.05. Bear in mind, right in the middle, we have z equals 0. So any value on the left would be negative, on the right would be positive. So you expect to get a negative value. So this table gives us the z values, specifically negative z values. And inside, we have the area. So we look for the value of 0.05. As we go down, we notice that 0.05 doesn't exist, but those two numbers, we have 0.05 somewhere in between. In fact, it shows with asterisk. If you look at the whole picture, you have access, obviously, to this table. So from there, you can read negative 1.6 on the left column. And at the top, you can read 0.04, 0.05, which means the number is in between, and therefore z becomes negative 1.645. This is how you do the reading from the z table with negative scores. Now, just in case, if the area to the right was 0.05, since you've done all of this work, for the right side would be the opposite of this, and it would be positive 1.645 by symmetry. It's important to know the total area again is 1, on each side is 0.5. If we want to use technology such as TI, second and vars variables, inverse norm, and you put 3 entries. Now, the area is 0.05, mu is 0, sigma is 1, and the result would be, of course, with a lot more decimals than we have here. Negative 1.64, and if you do the rounding as you did here, then you end up with the same value. Now we want to do the same thing. In this case, the area in the right tail is 0.1. We want to find the value of z for a standard normal distribution such that the area to the right is 0.1. And I always recommend you start with graphing. So even before you come up with the answer, you can expect a positive value. Remember, right in the middle is 0. Z-score of 0 means the value is equal to the mean value of the data. So with this being the case, we can subtract the value of 0.1 from 1. The total area is 1. So the cumulative area from the left, all this area, this portion is 0.9. So you look for 0.9 in the body of the table. And you notice that 0.9 doesn't exist, but obviously between these two numbers. So on the left side, you have 1.2, up here 0.08 or 0.09. So if you go in between, you can answer the z is between 1.28 and 1.29. We can pick 1.285. If you follow the instruction here, we put the area as 0.9, mu is 0, sigma is 1, and it results in 1.28155. Obviously, we have more decimals and a more precise answer. This is an approximation by using the table. Find the following probability. Probability of z larger than negative 0.82. Again, graphing is extremely important because at the very least, we know the answer must be larger than 0.5 because on each side, the area covered is 0.5, giving us the total area of 1. Now, here's the table again. You're looking for a negative value, of course, negative 0.82, which means this is the number on the first column. Look for 0.02 at the top, and it gives you the result as 0.2061. This is the area to the left, but we want the area to the right of negative 0.82. We are going to subtract that from 1. We get to the answer. The second method that can be done, if you go to the positive z-scores, and you draw positive 0.82 all the way from negative infinity to 0.82, you get to the same answer. By the way, the table shows that for negative 3.5 and lower, the table uses this number, 0. With 3 zeros and then 1 as the area. As far as the calculator is concerned, we use second vars and Normalcdf. We put 4 entries. So the lower entry is negative 0.82. But what about the upper? The upper, they put a huge number normally. And as far as I'm concerned, 1,000 is good enough. If you put even 100, it works out. I want you to know that. If you have any doubts, put like 10,000. because in essence, when we say probability of z larger than negative 0.82, it goes from negative 0.82 to infinity. However, since 3 standard deviations covers almost everything, therefore a fairly large number such as 1000 will do the job. Notice we end up with this answer. And again, we have a lot more decimals here than here, but if we stop here and do the rounding, you come up with the answer. By the way, be very careful when you do the rounding. Make sure you go to the next decimal to make a decision, and a proper decision. It's extremely important to know that 0.7938, when you stop at 8, you have to change it to 9 because of the next number being 9. Any number equal to 5 or larger to the right of that causes it to go up. Now, the z-value for mu for any normal distribution, it is always 0. The reason for it is z has the formula x minus mu over sigma. If you replace the x with mu, you end up with 0, which means in essence, a z-score of 0 that gives you a value equal to the mean of the data. Usually the normal distribution is used as an approximation to binomial distribution if NP, the product of NP and NQ are both large. How large is good enough? In some texts you see 5, in others you see 10, and in MOM most of the time they use 10. Find the area of the shaded region. The graph depicts the standard normal distribution for the bone density scores with mean 0 and standard deviation 1. So we want the probability of z larger than this number when mu and sigma are given. So number 1, right, mu is 0, sigma equals 1. Now you want the probability of z larger than negative 0.93. At this point, use technology, use table. You know how to use both of them. And the answer is 0.8238. You can use normal CDF, the technology, to come up with the answer. And you want to use as many decimals as possible, or at least pay attention to what they're asked. The graph gives us IQ scores for adults. They are normally distributed with the mean of 100 and a standard deviation of 15. So we are going to write this as mu equals 100, sigma equals 15. Pay attention to the fact that we are dealing with the population. That's why we use Greek letters. So we want the probability between the two numbers, 106, 132. So this is a normal distribution. We are going to go to standard normal distribution, or SND, using the z-score x minus mu over sigma. And what do we put in here? We already have the mu and sigma, therefore we use x equals 106 for one of them, x equals 132 for the other one. And now we put the z-scores of 0.4 to 2.133. When we graph, this is corresponding to 0.4, and normally I like to go with the graph of SND. So this corresponds to the z-score of 0.4, and this one corresponds to 2.133. And now again, use the table or technology and come up with the answer. Either way is fine. We end up with roughly about 0.3280.
Hey, Professor, can I ask a quick question?
Sure.
For the test, when we're showing our work for these, should we just draw a picture, and then if we're using technology, just like say derived with technology, or?
That's fine. Absolutely. For a case this simple,
Okay.
yes.
Okay, thanks.
Sure.
Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Find the probability that a given score is between negative 2.13 and 3.77 and draw a sketch of the region.
Excellent. So this is a good example to see how we expect this to be answered. So mu is 0, sigma equals 1. Here's the given information. Here's the graph. And the graph doesn't have to be perfect. An approximation is good enough. So probability of z between the two numbers, negative 2.13 and positive 3.77, is of interest to us. And at this point, it is up to you whether you use a table or technology. So as an example, if you use the technology in this format, the lower number you put it here, negative 2.13 for normal CDF. The upper value is 3.77, mu is 0, sigma is 1, and there you have it, again, of course, with much more decimals. So many more decimals, you decide how many decimals you need. If they don't ask for a specific number, 1 decimal is not good enough. You want to put at least 4 or 5 or more. Draw a graph and find P19. P19. What is P19? The 19th percentile. This is the bone density score that separates the bottom 19% from the top 81%. Therefore, start with drawing. The area to the left of some number is about 0.19. We are looking for this z-score. We are looking for this z-score. And it's important to understand that because the area is less than 0.5 and it's on the left side, ultimately the value should be negative. That's why the graph, it helps. And so with that being the case, if you go with the table, we don't have the area of 0.19. We have the area of 0.1922. We have the z-score of negative 0.87 for that. We also have the area of 0.1894. I hope you realize these two numbers, 0.19, 0.19 is in between. So the z-score for this one and the z-score in between this one, the answer should be really in between. Needless to say, this is a tad closer. If you go with the technology, you put the inverse norm with the area of 0.19, mu 0, sigma is 1. And there you have it. The answer is negative 0.87789. As I mentioned, it's closer to a negative 0.88. Fairly straightforward.
Three out of 8 drinkers acquire the habit by age 20. If 300 drinkers are randomly selected using normal approximation to the binomial distribution, find the probability that A, exactly 100 acquire the habit by age 20.
Perfect. As I mentioned before, we are dealing with word problem in statistics. So it's important to translate this as follows. What is given? Binomial distribution. If so, what do we need? N, which is 300, and then P, which is known as the probability of success, 3 out of 8. 3 out of 8 or 0.375. The next thing is we have to calculate the Q1 minus P is 0.625. We also have to show that the product of NP and NQ are large so that we can use the normal approximation. So normal approximation can be used now. So we are interested in BD, short for binomial distribution, probability of X equals 100. And remember, in the case of a continuous random variable, this will be 0 because it's a single value, whereas in a discrete case, binomial distribution is discrete, that won't be. So how do you go from a discrete to a continuous random variable? Statisticians use continually correction factor of a 0.5. Therefore, they go 0.5 to the right and left of this number. It makes it 99.5 to 100.5. And now we are ready to use normal distribution. From normal, the next one is standard normal distribution to go to the z value, which requires the formula. First, we have to find mu, which is equal to n times p, and then sigma, which is square root of npq, and therefore we can calculate the z-score using z equals x minus mu over sigma. So we calculate the mu, it was already done in essence. Sigma is square root of npq, we need those two, and we may need to use even more decimals. Calculating the z-score, so we x minus mu over sigma, we know mu, we know sigma, we are going to replace the x with 99.5 and the second time with 100.5, and we have two z-scores that we want. So from the normal distribution, after calculating the mu and sigma for binomial distribution, we get to the z-scores for those 2 points. And now this is SND, standard normal distribution. So we can graph, so it's somewhere between these two. And now, using the table, we come up with 0.0158. So you can use the table, or you can use the technology. If we are going to use the technology, Normalcdf, the lower value with, of course, more decimals here, and the upper value with more decimals, mu is 0, sigma equals 1, and it gives you the answer. To show how close we are to the actual value, we are going back to actually binomial distribution, and we calculate the binomial PDF for n being 300, p being 3 over 8 or 0.375, for the x value of 100. And here's what we notice. Look at all those three values. This is by normal approximation. This is the same thing using technology. Obviously, it gives us with more precise answer. And this is using binomial distribution. I hope you see how close they are. And the reason binomial distribution was approximated by normal distribution because of lack of technology in the past. Because it's very difficult to calculate it otherwise. Now, we are repeating the same question. The next part is asking for at least 125 acquire the habit by age 20. So we are looking at the same question, part B, and therefore we are repeating the same information from the previous page. It's a binomial distribution with n, p, q, mu, sigma. All of the values come from the previous page. Nothing brand new. They were all discussed on the previous page. So we are interested in calculating probability of x larger than or equal to 125, which means what? We want the probability of x equals 125 plus 126 all the way to n, which is 300. And this is exactly why they didn't want to do it with the binomial distribution. They did it by approximating by normal distribution. Now, we are going to use a 0.5 continually correction factor, which means this number, either we have to go to 125.5 or 124.5. I'm going to put both numbers and we're going to discuss that. So as we want to go from binomial distribution to normal distribution, either we use 124.5 or 125.5. Let's see which one and why. I want to go over that so you can easily pick. Remember the meaning of probability of x larger than or equal to 125. That means the first number is 125 discretely, the next one is 126, all the way to n, which is 300. So let's assume we go with 125.5. The first discrete number larger than 125.5 is 126, and we're going to miss that. However, if we go with 124.5, the first discrete number larger than 124.5 is 125. We are in good shape. Therefore, we're not going to use that. We're going to use 124.5. We are going to go to the standard normal distribution. So binomial distribution, normal distribution with proper justification. Go to the z-score, x minus mu over sigma, and here's your standard normal distribution. From the graph, you want the area to the right of 1.4311. And using the table gives us this answer. Needless to say, you can use technology. At most, 165 acquire the habit by age 20, which means we want probability of x less than or equal to 165. And let's do the same thing. So we can either use 165.5 or 164.5, one of the two. So to see what we need to use, understand less than or equal to 165 means probability of x equals 165 plus 164 all the way to 0. That is the meaning of it, which means the first discrete number is 165. Okay, so let us use 164.5. The first number, which is discrete and it's less than 164.5, is 164. So we are going to miss 165. This is not going to cut it. However, if you choose 165.5, the first discrete number, which is less than 165.5, is 165, and that works. Therefore, this is no good. So we go with 165.5. So that's the first thing. You want to have a justification. You don't want to make a mistake. What about S&D, standard normal distribution? You have to calculate the z-score. X minus mu over sigma, you plug in 165.5, you put it in here, and 6.3206. If you were to do the graph, 6 is way down here. And as you remember, within 3 standard deviations on both sides, it covers everything. On the left side, it goes to infinity. On the right side, goes to a fairly large number. So it's really 1 or 100%. If you go by the z table above 3.5, it gives us 0.9. How many nines? They use 4. Technology gives you a better approximation, of course.
IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120?
Excellent. Again, word problem. What did we get out of this? This is a normal distribution with mu of 100 sigmas of 15, and we want the probability of X larger than 120. We are going to go to the z-score, z equals X minus mu over sigma. Use the graph. So 1.33 roughly is here, and area to the right of it, that's what you're interested in. Technology table, either way is fine, gives you 0.0918, which means 9.18%. In this case, what is the maximum IQ score for the bottom 30%? That means the area to the left is a 0.3. So start with the graph. Here's a normal distribution. Put 0.3 on the left side. Again, it doesn't have to be perfect. Just remember, right in the middle, we have half and half, 0.5 and 0.5. So to the left of this value is 0.3 or 30%. We are looking for the z-score. And in this formula, if we have the z-score, we can calculate the missing X because we have mu and sigma as well. So from the table, the z is somewhere between these two numbers. From the table, z is X minus mu over sigma. If you do the cross product, X becomes mu plus z sigma. So mu 100 plus z. So you put negative 0.525, let's say, times sigma, which is 15, and it gives you 92.125. Now, maximum IQ score for the bottom 30% is 92.125. What is it that you really should remember in this case is that z equals 0 corresponds to mu. Okay. Therefore, which gives you the area of 0.5 on both sides, 0.5 on the left, 0.5 on the right. Because this is less than 0.5, whatever number you come up with must be less than mu. Technology, if we were to use the technology directly using inverse norm, the area is 0.3, mu you can use 100, sigma you can use 15, and in one shot you get the answer. And the reason it's slightly different, if you look at the first decimal, 92.1, they are identical, and then more decimals, they're completely different because technology uses more decimals.
Men have head breadths that are normally distributed with a mean of 6 and a standard deviation of 1. If a man is randomly selected, find the probability that his head is less than 6.2 inches.
Perfect. Thank you so much. So again, we are dealing with word problem. So what is given? Notice we have a normal distribution. ND, mu is 6, sigma is 1. This is the given. So we want the probability of X less than 6.2. Again, this is a normal distribution. Go to standard normal distribution by calculating the z equals X minus mu over sigma. Notice when you write the given, it becomes easy. Just plug in. And your X is whatever number that you have here. The z-score ends up being 0.2. Therefore, normal distribution becomes standard normal distribution. And a graph, so 0.2 is roughly here. So you want this area. As you can see, the area is a little bit more than 0.5 because remember, 0 corresponds to 0.5 on the left, 0.5 on the right. And you can look up the table. You end up with 0.5793. So the probability is about 57.93%. Now, what if we choose 100 men? Now, here's the thing I want everybody to pay attention to. This is identical with the difference that n is no longer 1. When n is 1, we use x. When n is anything but 1, a number larger than 1, 2, or any other number larger than 1, then we go with the x bar, probability of x bar less than 6.2. So what happens as a result? The formula for z is practically the same with a slight difference. N is 100, z is x bar minus mu of x bar over sigma of x bar. I want you to pay attention to this. Z is x minus mu over sigma. Z is x bar minus mu of x bar over sigma of x bar. Mu of x bar, the mean of sample means in essence, is equal to mu. But sigma of x bar is sigma over square root of n. So this equals mu. But this is sigma over square root of n. And therefore, this is a complex fraction. Square root of 100 is 10, divided by 1 over 10 means multiply by 10, and 0.2 becomes 2. And of course, probability of z less than 2, you are dealing with much larger area than this one. So this area, much larger. So the answer is larger than that, becomes 0.9772. If we were to use technology class, we would use Normalcdf. For the lower, since they have chosen, I didn't change them. If they didn't, I would put maybe minus 1000, because the lower is negative infinity. Please understand, it's negative infinity. So if you haven't touched it, they keep a very small number. This e means to the power. So that's why it's, and with a negative sign that is hard to see here, and that's fine. But if you were to choose, put just negative 1000. 6.2, mu is sigma, sigma is 1, and you calculate it, and it gives you the answer as you can see here. If you go with 4 decimals, they're identical. In this case, notice what I do. I keep the same mu. The sigma, I'm going to put 1 over 100 to the power of 0.5. I wanted to show you, even if you want to put it like that, you can do that. In case, needless to say, square root of 100 is 10, and we know that, but if it was something else that we didn't know the number, I wanted to show you how you put it in, and therefore you end up with the same answer, again, within 4 decimals. The main difference for part A and B. In part A, n is 1, you use x. In part B, n is not 1. It is larger than 1, and you use x bar, and it changes the formula for the z.
The assets in billions of dollars of the 4 wealthiest people in a particular country are 33, 29, 16, 11. Assume that samples of size n equal 2 are randomly selected with replacement from this population of 4 values. A, after identifying the 16 equals 2 to the 4th power, different possible samples, and finding the mean of each sample, construct a table representing the sampling distribution of the sample mean.
The idea of number of outcomes per stage to the power that is the number of stages. I hope you remember that formula. So when we do it with replacement, that means every number goes through the whole cycle, including itself. So what we have here, if we have, look at the top, we choose 33 with 33. We choose 33 with the next number 29, then 33 with 16, then 33 with 11. Look at those 4. Then we go to number 29. We choose it with 33. Then 29 with 29. 29 with 16. 29 with 11. Then we move on to the rest of them. I'm going to assume everybody can figure out what they are. Now, what is X bar? You just add them up, divide by 2. Obviously, the two numbers are identical. It becomes itself. The probability, if you go through the whole process, there are 16. So for each one is 1 over 16. So it's 1 over 16. For 33 and 29, the answer for X bar is 31, is 1 out of 16. You continue all the way to the end. So that's what you do. And then the sampling distribution of the sample means. Here's what you get. I want to make sure everybody understands how that works. We have two columns, X bar and P of X bar. This is not P, the bar is just at the top of X, P of X bar, P of X bar, like this one. If you look at 33, the answer is 1 over 16. But 31, take a look. We have 1 here. We have 1 here. So take a look at how it becomes 2 over 16. Needless to say, 2 over 16 is the same as 1 over 8. I don't want to write it as 1 over 8. I want you to see where they come from. So for a number such as 33, there is only one outcome, so 1 out of 16. But for 31, everybody, there are 2 ways to get 31, and therefore 2 out of 16. And you go over the whole process. This is what you get. So I'm explaining for a one that doesn't repeat is 1 over 16. For the one that repeats, 2 over 16. This is the sampling distribution of the sample means. Sample means. Compare the mean of the population to the mean of the sampling distribution of the sample means. Let's calculate the mean mu equals summation of x over n. If you go back to those 4 numbers, add them up, divide by size, which is 4. And the answer is 22.25. This is the mean of the population. This is this part. Now, what about the mean of the sampling distributions? That means you want to calculate the mean here, which has the formula summation of x bar, P of x bar. I hope you remember the formula from previous chapters. Mu of x bar is the summation of x bar, P of x bar. So that means multiply this one by this one by this one, all the way to the end, add them up. When you do that, what do you get? You get an identical answer. So mu of x bar, which is this one is mu of x bar, this is mu, they are identical, and they are both equal to 22.25. Do the sample means target the value of the population mean? In general, do sample means make good estimates of population means? Why or why not? The sample means target the value of the population mean. That is, the mean of the sample means, the expected value of the sample means is equal to the population mean. Mu of x bar, we showed, is equal to mu, and therefore it makes it a good estimator.
The population of current statistics students has ages with mean U and standard deviation, not samples.
Sigma,
yes. Samples of statistics students are randomly selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does the central limit theorem tell us about the distribution of those mean ages?
CLT, or the central limit theorem, one of the most important theorems in statistics.
The central limitation theorem, a sampling distribution of sample means, is a distribution obtained by using the means computed from random samples of a specific size taken from a population. For samples of size n greater than or equal to 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger.
Perfect. So the CLT is extremely important when n is large, and how large is considered large in statistics. 30 or larger, then that can be approximated by a normal distribution, meaning almost everything becomes a normal distribution, even if the original distribution is not, when you have a sampling distribution of sample means. Conclusion number one, the distribution of sample X bar will, as the sample size increases, approach a normal distribution. Number two, the mean of the sample means is the population mean. In other words, mu of X bar is equal to mu. The standard deviation of all sample means is sigma of X bar is sigma over square root of n. Therefore, for this question, n was 44, which is larger than 30. A sampling distribution of the mean ages can be approximated by a normal distribution with mean mu of X bar equals mu and standard deviation sigma of X bar equals sigma over square root of n. We replace the n with 44, therefore sigma divided by square root of 44. That is the synopsis of a CLT, central limit theorem.
A boat capsized and sank in a lake. Based on an assumption of the mean weight of 137 pounds, the boat was rated to carry 50 passengers, so the load limit was 137 times 50 equals 6,850. After the boat sank, the assumed mean weight for similar boats was changed from 137 pounds to 170 pounds. Assume the similar boat is loaded with 50 passengers and assume the weights of the people are normally distributed with a mean of 174.1 and a standard deviation of 35.1. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds.
Perfect. So first, the scenario describes a horrible situation that statistics wasn't at work. Now we want to put it to work, see what happens, and let's do the math. So it's important to see what is given as you look at and read the question. Obviously, we are dealing with a normal distribution. 50 passengers, n is 50, mu is 174.1, sigma is 35.1, and we are to calculate probability of X bar larger than 137 for this situation. So we want to calculate this. We use the z-score X bar minus mu of X bar over sigma of X bar. So X bar is 137. Mu of X bar is the same as mu, which is 174.1. But sigma of X bar is sigma over square root of n. So this number divided by square root of 50. This gives us negative 7.474. Therefore, the normal distribution becomes a standard normal distribution, probability of z larger than this number. If we were to graph it, becomes this. I hope you remember that when we go within 3 standard deviations, it covers the whole thing. So minus 4.74 is way beyond negative 3. So it's almost 100% or 1, which is horrible. Find the probability that the boat is overloaded. There is a 100% chance that it's overloaded when we have 50 passengers.
The boat was later rated to carry only 15 passengers, and the load limit was changed to 2,550 pounds. 170 times 50 equals 2,550 pounds. Find the probability that the boat is overloaded because the mean weight of the passengers is greater than 170, so that their total weight is greater than the maximum capacity of 2,550 pounds.
That's the same situation when you see a total capacity, for example, in an elevator, it works in the same manner. So with that being the case, we are dealing with again a normal distribution with the same mu and sigma, but n is 15 instead of 50. We want the probability of X bar this time larger than 170. We do the same thing. We calculate the z-score using the same formula here. X bar minus mu of X bar over sigma of X bar. Mu of X bar is the same as mu. Sigma of X bar is sigma over square root of n. We put it in. And we can graph this. Either way, by now we have an idea. Using the table or technology, we end up with 0.6745 or 67.45%. Do the new ratings appear to be safe when the boat is loaded with 15 passengers? Obviously not. No, because there is a high probability of overloading. The new ratings do not appear to be safe when the boat is loaded with 15 passengers. So we can use statistics to figure out the problem and resolve the problem.
At an airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 10 minutes. All of the different possible waiting times are equally likely. Find the probability that a randomly selected passenger has a waiting time of at least 7 minutes. Uniform distribution. A continuous random variable has a uniform distribution of its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape.
So that's the definition of a uniform distribution. Ultimately, you get to a rectangular shape.
Properties of uniform distribution density curve. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability.
Therefore, probabilities can be found by identifying the corresponding areas, and the graph using the formula for the area of a rectangle, area equals height times the width. I wanted you to see why things work out the way they work out by looking at this. So let's see what happens here. We know, according to what we just discussed here, the total area under any density curve must be 1. So the total area is 1. In the case of a uniform distribution, we are dealing with a rectangular shape. And in this example, from 0 to 10, the width is 10. So if the total area is 1 and the width is 10, then the height must be the reciprocal of that. So their product gives us 1. So all of this will give rise to this height being 1 over the width, which makes it 0.1. And therefore, we have this graph. So a quick recap. Here it goes from 0 to 10. Uniform distribution is a continuous distribution. The total area under the curve represents the total probability, therefore it's equal to 1. If the area is 1 and this is 10, this distance, then the height must be the reciprocal of 10, 1 over 10 or 0.1. What are we looking for? At least 7, the probability of X larger than or equal 7. Which means we want this part. And that would be the width times the height. The width from 7 to 10 obviously is 3, and the height is fixed at 0.1. And we end up with 0.3. So the probability is 0.3 or 30%.
Information regarding standardized tests used for college admittance. Scores on the SAT test are normally distributed with a mean of 984 and a standard deviation of 204. Scores on the ACT test are normally distributed with a mean of 20.7 and a standard deviation of 4.3. It is assumed that the two tests measure the same aptitude but use different scales. If a student gets an SAT score that is 65 percentile, find the actual SAT score.
So let's find out what's given. With the SAT scores and ACT both are in the normal distribution, let's write the values for mu and standard deviation sigma. So mu is 984, sigma is 204 for SAT. For ACT, the mean is 20.7. That means mu is 20.7, sigma is 4.3. First and foremost, we got the information. Now, the next one, if a student gets an SAT score that is 65 percentile, so let's see what 65 percentile refers to. If you go with the normal distribution, remember right smack in the middle is 0, on each side is 0.5. Because we want 0.65, it's a little bit to the right of it, how much we don't know, but the fact of the matter is this area is about 0.65. That's the meaning of 65th percentile. Then what do? We calculate we pick up the z-score either from the table or technology. So this will give us the z-score. From the z-score, for SAT, using this information, we go to the X. So area to the left is a 0.65. We need to find the z-score. After we find the z-score for SAT, we find the X value. How do we do that? Using this formula. Remember, z is x minus mu over sigma, cross product x is mu plus z sigma. So the key is to find the z. So that's the formula we are going to use. Mu is 984, sigma is 204. We got everything except z. We use the technology, area is 0.65, mu is 0, sigma equals 1, and it gives us the z value. Now, look at this formula. We have the mu, we have the sigma, we also have the z. Plug in. Whole number, do the rounding, 1063, 1063 is the answer. So a quick recap, 65 percentile gives us the area. From the area, we go to the z-score. Formula for the z-score gives us x, plug in, we have the answer. What would be the equivalent ACT score for this student? Well, we do the same thing, x equals mu plus z sigma, where mu and sigma come from ACT, and the z, we just found it here. So previous z, that means this one we just found, using the same z getting to x, but this time mu and sigma come from ACT. I hope everybody is clear as to what steps we are taking. Plug in. So again, a quick recap. We need to calculate x, mu, and sigma come from ACT, z-score from the 65 percentile is found here. Plug in. Here's the answer. We want only one decimal. So we change it to 22.4. If a student gets an SAT score of 1494, find the equivalent ACT score. Well, SAT, here's the information, mu and sigma. So what is given? the X value. Going to this formula or to this formula, we want to find the Z-score for this. And then we use the Z-score for ACT, and we come up with its X value. So SAT X is 1494. Find the Z value. Use the Z value to find the X for ACT. So this is the process, everybody. Z is X minus mu over sigma. So Z is 2.5. So the SAT score of 1,494 corresponds to 2.5. Z score of 2.5. That means we use the same Z score with ACT. Mu is 20.7, sigma equals 4.3 to find the X value. X is 20.7 mu plus Z times sigma of 4.3, 31.45. We want only one decimal. We get this answer, 31.5.